Good morning, nerds of Ignite. We are here to talk about Windows 10 security internals. Now, as you notice from the slide, I am the chief awesomologist at Microsoft. What does that mean exactly? It means that in the slide template, that's literally an open text field. You can type anything you want in there. So I did. But I want to scope it down. I want to make sure that what we talk about you understand is something that's interesting to you, because security means a lot of things. And one of my core missions is to demystify the things we talk about, because so many of the security features that get discussed are talked about almost as if they're magical security syrup. Whatever that security-ish thing is, it makes it better. So more of it's good. I want to disambiguate it. I want to make sure you understand exactly what these features are and why you want them and how we're going to get there. And the subset I've chosen to attack today comes from WDEG, which stands for Windows Defender Emmet's Gone. Some of you got that one. No, you may have noticed we have this whole guard terminology. So there's a whole suite of things that are out there, right? Windows Defender Application Guard protects your applications. Windows Defender Credential Guard protects your credentials. So naturally, Windows Defender Exploit Guard protects your exploits. So if you are in the sale and marketing of exploits, this is the feature for you. Hold on, I'm being told that's not actually what it's for. What this is doing is laying on top of Windows itself a way to apply security mitigations. And kind of where this, to me, fits into an end-to-end security story, we've been doing a lot of work across the Windows team and across Microsoft in application whitelisting. Some of you may have noticed that even in Azure, we have a new whitelisting feature that leverages AppLocker to do whitelisting on your server properties. It uses machine learning to help you build the rule set. On the platform, and we've got a session later on this week, my colleague Aaron Margosis and I will be talking about the whole whitelisting stack and a structured protocol to get to doing that. But that really is a major pivot in desktop computing, moving from I trust everything by default and I mistrust by exception. That's your antivirus solution. If I don't know you to be bad, you're okay. Which doesn't work in today's world. We pivot and we say, okay, I'm only going to run you if I know you to be good. But that's just going to stop, hey, do I load this XE, do I load this DLL? What if the thing itself is poorly created so that the adversary is able to inject their own malicious code? They don't need a DLL, they don't need an XE, they'll just run happily and party inside of your process. So how do we go about and fix that, right? So we're really taking a subset of the whole defensive stack in Windows and breaking it down to what does Windows itself provide? And what Exploit Guard is doing is twofold that should be really interesting to you. Number one, it gives you access to memory mitigations without having to go back and recompile all of your stuff. Because how many of you, if asked today, please recompile all of the applications you're currently running in your environment, due date of Tuesday, would successfully meet that goal? Right? Recompiling it all is really tough, particularly when you think about the size and scale of enterprise software catalogs. The average age of enterprise software today is 12 years. 12. That means half of it's older. And roughly 50% of all code running across all enterprises today has some VB6 sitting inside of it. So we're dealing with a big legacy challenge that heretofore was really difficult to address. Emmet began to address it. We wanted to formalize that. Now, if you are familiar with Emmet or the Enhanced Mitigation Experience Toolkit, it had a bit of a clunky UX. What I want to do is show you what we've done to replace it. So this is coming in the next iteration, the fall release. If you go into the Defender Security Center, open up app and browser control, open the exploit protection settings. Some are system-wide, set your defaults, but you can also program by program apply a set of mitigations. Now, what was really amusing to me is one of the biggest sources of delight for the team that was building this was when they got to say, we got a UX designer to actually create a UX for us. We didn't have to make our own. So actual UX designer, and here's a list of all of the things that you can do with Exploit Guard, what's been applied in this process, and you can configure this. Basically, turn on a protection for an app that's already been compiled and may not have chosen to put that on. For various reasons. Maybe the developer didn't know about it, or in some cases, because it has an extensibility model. For example, Internet Explorer, the extensibility model, is a binary extensibility model. ActiveX is jack a DLL into the process and let it run. So it's not about IE itself not working with memory mitigation features. It's about all of the plugins you have potentially breaking because they're all subject to those rules. But I can put it on if I'm sure that my catalog is safe and okay. The challenge that I want to surmount today is I don't think that those 5 to 10 words that you get really help you decide whether or not you want the feature. So we're going to explain them all so that you understand what are these features and how can they help me. So we're going to go down the list because I want to make sure you understand what all of these things are. This is the defensive stack of Windows. The first one we call arbitrary code guard because we really like the word guard. What arbitrary code guard does is it makes sure that you don't mark memory as executable. Just arbitrary things to let them run. And it does that when you're calling the Windows APIs to allocate new memory. The virtual alloc function, the virtual protect function, you don't have to know the C++ functions, but I'm just giving you a little bit of internals detail. Whenever you call them, if you try to mark it as executable to put that flag on, we'll just say, no, we can't allocate that memory. So you can't mark any additional memory as executable to block you from running arbitrary code. Well, there's an interesting side effect to that, is that there are plenty of applications that leverage the use of arbitrary code generation. Anything that does JIT compilation, for example. Now, I know probably none of you have used any platforms that use JIT compilation like .NET or Java, but there are some out there that use it. But I want to give you a particular use case of where we had to go back and refactor software to support this. Microsoft Edge will JIT compile, because that's how you do JavaScript. JavaScript is just a scripting language that gets written out to assembly language in order to execute. And in order to get that to work, we had to move the Chakra JavaScript engine out of process. And we had to move the Windows Advanced Rasterization platform out of process. It was a design change for us to support it. But arbitrary code guard then protects the process itself from new things running. So if I have software that doesn't need to generate code and execute it, arbitrary code guard can keep those things from running by stopping it from being marked as executable. Our next protection, blocking untrusted fonts. This one's relatively straightforward. If it's in Winder/fonts, it's okay. If it is anywhere else, it is not okay. Very simple. This used to be a separate independent feature. Right now it's something that we have built in directly into the platform. Right? Really good protection because fonts have been used as an exploit mechanism in the past. This lets us block it. Because it has a potential compat impact, I can go app by app and choose it. Next mitigation, which is actually a really good mitigation, but it has to be compiled in. ASLR, which stands for Address Space Layout Randomization. And I'll try and pick an example of something that's running on my box right now and see if I get lucky on something that's been relocated. The idea behind ASLR is, who should I pick? I'll pick on Apple here. Yeah, so and they've got everything compiled with ASLR, so everything is awesome there. So they've compiled it that way. which means the binaries inside of there will get moved around. The idea is this. In the past, when we would load certain modules in memory, we would put them in exactly the same location every time. In fact, that was a recommended practice for a while. If you were writing code back in the days of Petzold and Richter, has anyone been around that long? Have those books on your bookshelf? A couple of folks? I'm old. By the way, Jeff Richter works at Microsoft now. That was one of the more exciting discoveries I made in the past couple years. Back in those days, we would say, put them here, because if a DLL does not land where it wants to go, it has to be rebased, which means we have to go through the DLL and adjust all of the pointers within that DLL to the new location. That takes time. It's a performance hit. So we optimize to say, always be in this spot in memory every single time. Well, if you're a bad guy and you know a chunk of memory that does the thing you'd like to get done, and it's always in the same spot, you just need the instruction pointer to point at that bit of memory. You know the target location. It is static, and that makes it easy, and it is being actively used. ASLR says, no, don't always be in the same space. Move around so I can't put it where you want to go. But it's opt-in, because there's a potential app impact from leveraging ASLR. So you have to specifically choose it and compile it. If it's not compiled, right, how can you address that? Because not everyone says relocation is okay. I don't have it put in place. I'm most effective when everything is randomized. How can I go about achieving that? Let's go back and take a look here and talk about something called rebasing. So this is Process Explorer, and in Process Explorer you can add a couple of columns, the image base and the base where it actually is. So the image base is what's compiled in. Remember that recommended practice of here's where I'd like to go in memory? We say in the compiler, we'll just go here. This happens to be a default, right? So no one ever went through and rebased it and adjusted it. It got there and someone else was already there, so it had to be moved. So Process Explorer highlighted it in yellow for us and said, oh, I moved this one. That's rebasing, and it happens all the time. So in order to implement ASLR retroactively, what do to get ASLR behavior? We stick something in the way. Oh, you can't land there. I'll have to move you somewhere else. Problem solved. So forcing ASLR just sticks something in the way and rebases the DLL. And therefore can get you that most effective mechanism of, hey, memory doesn't look the same across every single run that you have. Super effective. There's another flavor of ASLR, which is bottom-up ASLR, which we also don't really thoroughly explain, but it's also actually a relatively straightforward concept. For bottom-up ASLR, we address the challenge. Well, actually, we'll go back to mandatory ASLR. The challenge here is I can stick something in the way, but if I stick something in the way, it's actually fairly predictable where you're going to end up going. I can figure out those algorithms. So now you're not going to be in the place that the compiler says, so I can't look at the binary and determine where it's going to be. But at runtime, you'll be at the same place time after time, and I can predict that. So bottom-up says, let's address that by allocating a random number between 0 and 256, 64K allocations of memory that are also in the way. And because it's randomized, I don't know where you're going to end up. It's whatever spot happens to be next, to inject additional randomization in where those things get put in place. So now in your toolkit, you have the ability to apply this additional randomization to start to break that particular adversary tactic, which is one that's commonly used, right? ASLR really common. People aren't compiling that way. We'll just kind of stick stuff in the way to get it to happen anyway and just rely on DLL rebasing. Code integrity guard, another per process feature. When you are loading a library, it just injects a couple of additional checks. First, it will validate that you have a valid signature. And second, It will validate that you're in a valid location. You are in an admin writable area and not in downloaded program files, not in the downloads folder, not anywhere else, but in one of those locations. You just won't pick it up and run it. Potentially a pretty big compat impact, because how many people can accurately claim that 100% of the software they run in their environment has been digitally signed with a trusted signature? I got laughter. For those watching the recording, right? Basically a few snickers of, yeah, that doesn't seem very likely, right? If everything is signed, I can do this. If it's not, then I have a challenge. I may not know. I actually, at this point, want to branch into one of the features that I think is really key to what we've built in exploit guards. If I go back in here, and I'm going to pick Code Integrity Guard as the example, this is the killer feature. Because how many of you get terrified turning on a security feature and hoping for the best? We have an audit mode. We're just going to log a warning. Hey, this would not have loaded if this feature were enabled and enforced. So now I can start to build a process that will start with enable it in audit mode, monitor and collect. Incidentally, as we'll see later, this will show up if you're using Windows Defender ATP. It surfaces there, so it's not just device by device. Yes, it's in the event log, but yes, it also is surfaced and can be subscribed to see what will be the impact to my environment if I enable this. Auditing allows me to do exactly that. So I can check, is Code Integrity Guard going to be blocking for me? This does not have very good range on the clicker. The next control, this is a security control that got a lot of conversation. Because when we first were talking about the end of life for Emmet, right? If you want, I'll give you a little bit of the backstory behind what happened behind the scenes with Emmet. One of the things we wanted to fix is we didn't want you, our customers, to feel like you had to solder onto the side of your Windows something that kind of didn't really look and feel like Windows in order to make it secure. That didn't make us happy. And then there was a lot of folks who had that sort of that magical security syrup theory that were like, well, we've got CFG. CFG is better than everything that's in Emmet today, so just go use that instead. We don't need anything anymore. And as we've been unraveling today, as you start to understand the mitigations, you realize I can't just swap them out and say this solves everything. What Control Flow Guard will do is it will just protect certain things. So we made the case, right? Communally, worldwide, the globe came into place and said, here's what I'm trying to fix. We had all kinds of different outreaches. You may have participated in them, and we talked about, hey, these are the snares that I use it for, so that we can better define what eventually became what we call Exploit Guard. That came from a partnership with all of you, because what you find once you dissect Control Flow Guard is that it can't protect everything. So there's all kinds of little details here in the deck, but I figured I'd rather explain that one in demo. Now, one of the bits of feedback that I've gotten from folks when I've given this session in other locations is, listen, Chris, we see entirely too much console mode debugger and not enough PowerPoint at events like this. Right, so if you can please hurry through that and get to the PowerPoint, we'd really appreciate it, because not enough PowerPoint. So I apologize for yet another console mode debugger session, but it really does help to illustrate the point. Now, oh, where did my pen go? I have, somewhere along the line, lost my pen. That's unfortunate. All right, well, I guess I won't be drawing things. We'll do examples. So I'm just going to unassemble a function. Now, it's not traditional to spray a bunch of assembly language on the screen, but honestly, I think we can get through this and come up with a really great understanding of what it is. Oh, did you find my pen?
Not yours?
That is amazing. Or is this someone else's pen that I just stole? Oh, now I own your pen? I'm not giving it back. All right. Yeah, I think I dropped it on the way down here. We'll see if I can trace it down. Otherwise, I may be out $100. All right, so let's go this. So here I've unassembled a function. I'm not going to dwell on it, but I'm going to briefly talk about some of the concepts of assembly language. This is a function, and the way, let me see if this works. I'll get a sketch pad. The way the CPU works is you have an instruction pointer. It happens to be the EIP register on 32-bit processors. We'll just start at a point and execute instructions. And they will be things like add, which is adding two numbers together. Move memory from one location to another. Subtract, or even jump. That's go to, like in BASIC. Relatively straightforward. We're just following along and executing one after the other after the other. It's linear, right? But we have the concept of call, and call will actually move you to another spot in memory, execute some more instructions, and maybe they add and subtract, right? And eventually they will return, and the return, or ret, will bring you back to the next spot in memory. It's all very linear. You can trace the flow of instructions. That's how it works, right? So it's relatively straightforward. If you've done even basic programming, this should make pretty clear sense. Now, if I want to run code of my choice, there's a couple of different places I can attack. I can attack the jump instruction and say jump and fidget with an address in here. But that's generally a little bit harder than fidgeting with the call, because a call can be either call at address 12, or it can be call at whatever memory address 12 points to, and address 12 may point to address 38. The second one's called an indirect call. It says whatever this variable points to, jump there. So if I'm an adversary, that is generally the easiest place for me to do it, because oftentimes these instructions, modifying a jump instruction, that's not in writable memory, so I can't directly address it. That's why that's harder. But if I'm calling an address of a function, that's writable memory, the adversary can overwrite it, because writes are allowed, and put something else there. That's why they attack it. So how do I protect against that? And if you look here, this is exactly what's happening without the protection. Call whatever this is pointing to. And hopefully it's pointing to someplace good. Here's what control flow guard does. We still have call whatever address that's pointing to, but before we do that, we've added an additional call this function, which is the guard check. Is this a safe place for me to call? And if it's not a safe place for you to call, it will jump on out. Because we're asking whether or not it's a safe place to call, we need to determine, is that actually safe? How do we do that? At compile time, we produce a bitmap. Here's a call target, here's a call target, 1, 0, 1, 0. If it's a 1, it's okay to call there. If it's a 0, you cannot call there. We generate that at compile time. So let's put this together. I have to insert instructions and build a database. That has to be done at compile time today. Inserting the instructions, if it is for a Windows function, we could jack those in, but without it being a Windows function, we have no means to inject code in there. And we also have no means to safely build the bitmap of all the safe callable locations. That means you have to have compiled with that, and we're back at the original problem of I can only apply control flow guard for stuff I'm compiling new. So it doesn't protect all of my existing stuff. That's why it's not a suitable replacement for everything. But it's really good when it's turned on. It's one of the most effective mitigations we have against return-oriented programming. So that is the background behind that. There's also, even for brand new stuff, a cost associated with this. Now it's a bitmap, so checking to see whether is it a 1 or a 0 is what we call an O of 1 check. That means it is constant speed. No matter how big your program is, no matter how many jump locations, it always goes exactly the same speed. And that's good, right? Because O of n means the bigger you get, it increases linearly, n squared means it increases exponentially, kind of digging back to some of the computer science concepts. This will always be the same speed. But the speed it runs is not 0. In fact, if you look at an indirect call today, on average, an indirect call that takes place in, normally, without this compiler option set, it's going to take about 14 CPU cycles. If you apply CFG, it jumps up to about 40 CPU cycles. 40 CPU cycles is not a huge amount of time, but it is roughly double the amount of time that it took me to do it without CFG. So we are still seeing that not everyone is enabling it even when they can because they're not meeting their perf gates, right? And compilers will need to evolve to generate fewer indirect calls in order to make this more and more practical. And that's the challenge we've got to overcome. In the interim, we have a lot of other things. So CFG, very good, but compiler dependent. So far, so good. Did I go too far with the assembly, or was that useful? Is everyone's eyes are kind of like glazed back in their head. But it really illustrates it well. Here's why we have to do it that way. Let's go on to the next one, data execution prevention. This is one that's been around since XPSP2, but I just want to make sure we understand exactly what this thing is and what it's protecting against. Because we talked initially about arbitrary code guard, which blocks me from marking new things as executable. Well, with that, I need a separate control that stops me from executing memory that isn't marked as executable, because without the pairing, the first one's not effective. What data execution prevention does is it ensures that if I have not marked it as executable and I stick the instruction pointer there, that I won't execute it. And a very common attack is this. Right? This is going to be a Stack Overflow, which was really, really common, a decade or more ago, and still pops up. How do I use a Stack Overflow to execute things that I want? In this example, I'm going to provide arguments into my function that are going to go longer than I've allocated memory for. I have allocated 8 characters, and the adversary gave me a lot more. And so we just started walking their input and marking it on and sticking it into memory. And we walked through, right, the space I had allocated, right? So that shows up, how do I mark on this? You can do it there. Pen, right? So I put my initial A's there. Actually, let me put it in. I put my initial A's, but then I still had more. So my yellow A's in the input went into the next variable. I just kind of kept walking up the stack. And I still had more A's, so I went to the next variable, and I kept walking up the stack until I got to the return address, which is where when I get to the return instruction or ret instruction, that's where I go back to. They're able to overwrite that. Now, we haven't stopped that from happening, but if that bit of memory is not marked as executable, and I don't block executable code from running, now I've set the instruction pointer at my own memory, and I'm running whatever I want. dep's going to block me from injecting the code as part of the input. And it will block that, and there's hardware support for doing that. So data execution prevention is something that's fairly pervasive, right? So this one's getting safer and safer to enable, right? But a really effective memory mitigation in Windows. We have the ability to disable extension points. Something that's happened over the years is that Windows grew more and more extensibility points. So I could do things like put in app init DLLs. When I'm initializing an application, it'll just load up another DLL as an extension point. But a lot of people aren't keeping tabs of those AppInit DLLs to see if they're safe. It's a hiding place for an adversary. Things that don't go noticed. This will stop it from being loaded into that process. Windows hooks, commonly used thing. In fact, we had an issue working with one vendor where they used Windows hooks to get notifications. It was actually, if you remember back in the day when, some of you will, when we used to get CDs in the mail to install software to connect us to our online world. That organization eventually realized that not everyone used the browser they provided in their software. So they've used Windows hooks to plug in to the browser and just said, hey, when you close, notify me so I can ask if they want to hang up the phone because you were getting charged per minute, right? Sort of a nice user feature. That's the kind of things that Windows hooks would be used for. Give me a notification. Disabling them says turn them all off. Don't wire this, don't run this code so that I don't have all these extensions running inside of my software. I can disable calls into Win32k. This is a way to jump into system context. That's what Win32k does. So if my application should not be calling directly into Win32k, most shouldn't, I can simply disable it and make it so that that's no longer possible. So I can't jump into kernel mode from within that application if it's likely to be compromised. I can block child processes. So anytime I try to call the create process API or anything that calls the create process API, that will be blocked. So if I shouldn't be spawning a new process, if I shouldn't be spawning a new instance of PowerShell.exe, or all of the other tactics that are happening, because this is part of the threat environment that we live in today, is the living off the land movement. I want to put as little malware as I can on the device. Just enough to get me started, and then fire up a process that's already there, and once I've fired that up, now I can start living off of what you already have on your device. This will stop me from launching that new process. So now I can't fire it up. I can block remote images, application by application. So a remote image is I'm trying to load a DLL, and that DLL is coming from a network share or coming from an HTTP destination. That's allowed by Windows. This will block it. So the load library API will no longer call it at all. Or similarly, I can block low integrity images. So a brief review on integrity levels, and for those of you who are deeply interested in going into the depths of Windows security, last year's talk on security internals goes into all kinds of depth of what integrity is. I'm going to kind of give a simplified overview. The concept of Windows integrity levels is putting in tiers of trust for software, to do authorization based on how much you trust the process, not just identity. So if we look here, these are actually low, but they are both low integrity and they're app containers. So if I go in and look at the integrity, it's actually low. So all of your modern applications will run at the low mandatory level. So if I open up a web browser, right, I'll just fire up Edge. Here's Edge, Edge content processes. They are running at low. Right. Similarly, if I fire up, whoop, I didn't want Cortana. I'll fire up Chrome. Let's get that started. And there's the low. And actually, technically, they went a little below low, and they went all the way to untrusted in their content processes. But the basic idea is this. We have different levels of trust that extend from untrusted, low, medium, high, and system. So I have tiers of trust. Low generally means I'm coming from an untrusted environment. So low integrity could be my web browser, right? Most modern web browsers today, with one notable exception, run in low integrity or lower. Office running in protected mode runs in low integrity. Adobe Reader runs in low integrity. If those drop any files, this mitigation will block loading those into your process. So now anything that comes off the web is not going to be then jacked in. So if I use the web browser as an attack vector, then that gets blocked as a means to be loaded into the process of an existing application. Export and import address filtering. Here's another one we're going to dive a little bit into the internals of how Windows works to make sure we understand what that can and can't do. So for that, let's get these windows out of the way, and let's pull open, we'll do import tables first. So the way Windows works, right, it's good to know this at a conceptual level, is I'm going to have an executable that links to a bunch of DLLs, and those DLLs can change over time. And they can move. We already talked about ASLR, we talked about rebasing, so I can't just say, go over and run this function which is at this address. I need to be able to dynamically adjust as time goes on. How do you adjust? You adjust by having a layer of indirection. So this is what's called the import table. So I just have a list. Here's all the functions, and here's the address in memory. We don't know them yet. But as the loader loads them into memory, it fills in the blanks. It will actually put in place, here's where this one is, here's where that one is, here's where that one is, here's what that one is, and make sure that, hey, and now I have it actually translated. There's also the concept of modification of the export table. And to understand that, got to understand this little bit of magic that we put into Windows binaries at the beginning. We actually initially put this in place to support hot patching. At the beginning of every function in Windows, you will see this function, move EDI, EDI. Let's translate that from assembly language to human. Right? What does the move function do? It moves memory from one location to another. So if I move the contents of the EDI register into the EDI register, what has happened? Nothing. Nothing has happened. That's like copying something to itself. So that's a no-op. So why on earth do we write it that way instead of just nop, nop, nop? Because that is the highest performance way on an Intel processor to do no-op instructions of enough size to inject instead a jump function. Because if you use a technology like detours from Microsoft Research, or the approach has also been described in a lot of other technical papers, you just replace that functional no-op with a short jump instruction, and now you can redirect at the export table. So import and export, that's how we link those things together. And since that's an opportunity to take control, how do we protect that? So with the export address table filtering, what we do is when you enter critical Windows functions, right? So it's got to be in Windows in order for us to run code, in order for us to run a check. When you enter a critical Windows function, we will make sure that the caller is in memory that belongs to the program and not dynamically generated memory. And on the export address filtering, we will make sure that the export table, all of those addresses, exist between the beginning and the end of the DLL. In fact, this is a technology that's been in place and in use for many, many years by people who write games. Right? So a lot of the anti-cheating code in games will use import address filtering to make sure that you don't stub out a call to get the player's aim at the other player and replace it with aim directly at the other player's head so that the person wins. That's how anti-cheat software is implemented. So we put in that filtering to make sure that, hey, if you came from a known good location. We have the ability to simulate execution. This allows us to protect the return. When you get to the return from a Windows function, we can actually go and look at where that address went to and execute a few instructions and make sure that it is in a valid place in memory. There's a little look ahead before we actually move on and execute those instructions. We can validate, similar to the import address filtering, that the call into critical functions in Windows actually came from a call instruction versus a return instruction. You shouldn't be returning to Windows when you're entering a function. That should be coming from a call. Again, looking at protecting against a common adversary tactic. Validating heap integrity allows me to put in additional controls for the heap, to put in some additional randomization on heap allocation, to put in guard pages and put in additional protections around the heap. We also have structured exception handling override protection. This is another attack vector that adversaries will use. Again, their goal is to run arbitrary code. How do we go about running arbitrary code? Here's another mechanism. If I'm able to register myself as an exception handler, as soon as you hit an exception, and conveniently, right? Exceptions happen fairly frequently. When I hit one, then it runs through the entire chain of exception handlers, because there can be more than one. We have them chained together. It's a simple linked list. We go to the first function, we execute the handler, we follow to the next function, we execute the handler, follow to the next function, execute the handler, until we get to the point where we say we're done. And what structured exception handling override protection will do is it will put in a validation frame at the end of that linked list. And then when we process the exception, we'll actually chase the linked list through to the end to make sure that we actually end at that validation frame. Walk it through, look at each individual component, and make sure that we get to a valid destination. So that now if I've injected something in the middle and I haven't actually then linked forward to whoever was next, I don't end up at the actual validation frame. I can validate handle usage so that when I hand something over, I can ensure that that actually is a legitimate handle and not an arbitrary point in memory. Some of that is provided by default because some of that will happen automatically if that handle is in the very, very beginning of memory to protect me against null pointers, null handles. But this will actually validate that it is a legitimate handle that's been allocated in the right way. Now here's one that I'm not sure I've yet thought of the scenario where it's actually useful to real people. Outside of Microsoft, that is, right? Validate image dependency integrity will ensure that if I'm going to load you, the load library API, that you are digitally signed with a Windows certificate, which effectively means I can never load a DLL that's not a Windows DLL. So if you have any DLLs, this will cause you to fail. But if you just are a simple exe only linking to Windows binaries and that's it, maybe it's useful there. This is super useful for Microsoft Edge. I mean, a lot of these things are already in use by Edge. And everything inside of Edge is going to be signed by Windows. So very useful, very helpful there. I'm not sure how generalizable that is. So Verdict is still out on whether that's something that you'd want to even invest some time fiddling around with, but something that clearly you can see where we'd use it internally for our own stuff. We have the ability to validate stack integrity. This is another adversary tactic that we've been seeing a lot lately, which is if I cannot manipulate your own stack, a stack is nothing but a contiguous bit of memory that follows a set of rules in terms of how it's formed. So if I don't like the things that are on your stack, I want to run a different set of things. Rather than try to modify your entire stack and not get caught, what I will do is get a different chunk of memory and format the contents of that memory as if it were a stack, a shadow stack, if you will. And then with the shadow stack, as soon as I get the instruction pointer pointing onto the shadow stack, all of a sudden, I'm running whatever you put on your alternate stack. I've gotten control of the flow of code execution. So we can detect when, again, you're calling Windows binaries, if the current stack has actually been allocated as a stack and is not some random piece of memory that happens to look like a stack. That, ladies and gentlemen, is the gamut of protections provided by Exploit Guard, all provided with friendly group policies that you can enable, with a friendly user interface that you can enable, and really, no, thank you. Edit. Right? A much better way of controlling mitigations than we ever had with Emmet. This is above and beyond what we ever had before for providing very, very advanced levels of protection. And to re-emphasize the earlier point, very critically, we also provide auditing. So with mitigation auditing, I can see in the event log all of the things that I've done, all of the things that I've changed. This is all, I don't know if it's actually been fully documented yet. I'll look that up. If not, it will be before we ship it. But all of the event codes. So if we dive deep into what's being listed here, we can see the event ID. A little tip. That event ID will always be one off depending upon whether it was in audit mode or in enforce mode, right? So in this case, we can see, hey, I had this particular mitigation enabled because it's a not Microsoft signed binary. This one was a warning, so it was 12. It'll be off by 1 if it were actually blocked that way. So I can start to gather those and look for my odd numbers and even numbers to determine what was audited, what should block me from moving forward versus what was actively blocked, what protected me. And as mentioned, it will also show up inside of my security center online so I can get aggregated information on what was happening. And it is also all controllable through Windows Intune. So I can configure Exploit Guard through Intune as well. And I tried to get a screenshot of that, and I apologize for not having that there, because that, again, it's been an evolving feature set, and I wanted to get something accurate and current, but all easily controlled. So that's the defensive stack that you have for memory mitigations, a really critical thing to think through the strategy, right? So as we kind of recap and rewind to the beginning, right? Here's what we're trying to build as a platform. First of all, we need to get software mistrusted by default. The application whitelisting is core and central to everything. Core and central to application whitelisting, by the way, is not having everyone running as administrator. Because you can't effectively control with whitelists if everyone has control over the whitelists themselves to turn them off. So I remove admin rights, I get application whitelisting enabled, I trust software by exception, and now I have a whole host of tools I can apply to protect the memory inside of that software from being compromised by the adversary and leveraged to their ends. And that really does continue to raise the bar and make it harder and harder for adversaries to attack your platform. So hopefully you like it. I wish you success in getting this enabled and further protecting your Windows devices. Thank you very much.